time,
Mm-hmm.
wouldn't it be plus 3 times 4c4?
Yeah, that's what I was looking at. I agree. That should be 3 times 4. I think it should be 3. Yeah, it should be 3 times 4. Yep. Okay, good. So okay, that should be there. Okay, so f double prime of a is 2c2. Okay, and so if you apply this, if you keep doing this, meaning solving for f, the nth derivative of f at a, you get this relationship. Okay, what you observe is that the nth derivative of f at a is equal to n factorial times c sub n. Okay, so look, so if you take the first derivative, you get 1 factorial times c1. If you take the second derivative, you get 2 factorial, which is 2 times c2. If you take the third derivative, you get 3 factorial, which is 6 times c sub 3. And so if you keep doing this indefinitely, you'll get that the nth derivative of f at a is equal to n factorial times c sub n. Okay? So then, solving for c sub n, you get that c sub n is equal to the nth derivative of f at a divided by n factorial. Right? Okay, and so what this proves is this theorem, that if f has a power series representation at a, then its coefficients are given by the formula c sub n, which is equal to the nth derivative of f at a over n factorial. Okay, so that's what we just showed. And so let me generalize this. Our conclusion then is that if f has a power series representation at a, then it must be of the form of this form. F of x must look like this. F of x must equal this expression. It must equal the sum from n equals 0 to infinity of the nth derivative of f at a divided by n factorial, that's the coefficient c sub n, times then x minus a to the nth power, because the sum of these things with coefficients, and the coefficients are of this form. Okay, and the way you can think of that sum, if you were to expand it out, it would look like this. It would be f of a plus the first derivative of f at a divided by 1 factorial, divided by 1 factorial, plus the second derivative of f at a divided by 2 factorial. That's why I thought the x minus a here, and then times x minus a squared, and then continues plus dot dot dot. Definitely. Okay, so if f has a power series representation a, then it must be of this form. F of x is equal to that sum. Okay, and so we're going to call this statement 6. This is statement 6 in the textbook for this section. Okay. So the series in equation 6 is called the Taylor series of the function f at a. At a, or center, or about a, or centered at a. Okay. For the special case where a is equal to 0, Taylor series becomes the following. And so I'm going to call this 7. This is 7 in the textbook in this section. So if A is 0, then you get a Taylor series centered at 0. So you have this sum, except A is 0. And so now it's just x to the n. Now it's just that. And here A is 0. So you get that sum. And then the way to write that out would be equal to f of 0 plus the first derivative f at 0 divided by 1 factorial times x plus the second derivative f at 0 over 2 factorial times x squared plus dot, dot, dot. Okay, so that would be the Taylor series centered at 0. So this case occurs frequently and has its own name. It's called a Maclaurin series. Okay, so a Maclaurin series is a Taylor series centered at 0. Okay, and I should note that there are functions not equal to the sum of their Taylor series. So it must be what's called representative as a power series about A or centered at A for this to occur. So a Taylor series is not necessarily a representation of your function. A Taylor series is a sum of this form. And so some functions are equal to its Taylor series and some functions are not, okay? Assuming a function is equal to its Taylor series, then you know the coefficients are of this form, okay? Okay, so far we are starting with the assumption that it can be that it has a power series representation to find it, okay? So right now we're not showing that it does have a power series representation. We're assuming it does, and we're finding that representation, okay? Example 1, find the Maclaurin series of the function f of x is equal to e to the x and its radius of convergence. Okay, so this does have a power, e to the x does have a power series representation, and so we're going to find it centered at 0. Call this Maclaurin series. Okay, so we have f of x equals e to the x, and so if you take the nth derivative of that function, right, then it's still equal to e to the x, right? Because e to the x, the derivative of e to the x is itself. Now, if you take the nth derivative of f at 0, you get e to the 0, which is 1, right? You just plug in 0, get 1. And this is for all n. Okay. Therefore, the Taylor series for f at 0, or its Maclaurin series, is, so f of x is equal to the sum from n equals 0 to infinity of the nth derivative of f at 0 divided by n factorial times x to the n. And so that's equal to f of 0 plus f prime of 0 of 1 factorial times x, this sum, right? So you might want to think of it this way. Before you can visualize what the summation is, maybe you want to write out the terms like that so that you know what the notation is representing. It's equal to this. Now f of 0, these are all 1s. This is 1 plus x plus, this is a 1/2 x squared plus, then it would be 1 over 3 factorial, which would be 1/6 x cubed plus dot, dot, dot. Okay. But actually, I'm going to write it this way. It's this plus dot, dot, dot. This is divided by 1 factorial. Let's see. This is divided by 0 factorial. Okay. And so you get that power series. You get that Maclaurin series. Okay. To find the radius of convergence, we let the terms a sub n equal to x to the n over factorial. Okay. Then, well, what do? You take the a sub n plus 1 divided by a sub n. Okay. And so you want to find the limit of this. So first, the a sub n term, a sub n plus 1 term is x to the n plus 1 divided by n plus 1 times, well, so it's divided by a sub n, which is x to the n over n factorial. Now, if you take the first thing and divide by the other, it's the same as multiplying by the reciprocal, right? So you have this fraction divided by the other one is the same as multiplying by the reciprocal, which is n factorial divided by x to the n. Just gonna get rid of this. There we go. Okay. This is n plus 1 factorial. Okay. Divided by that, and so you switch. Dividing by a fraction means multiplying by its reciprocal. And so now x to the n plus 1 over x to the n is x. And then n factorial over n plus 1 factorial is n plus 1. So you get that. But now if you take the limit of that, if you take the limit of that, it's 0, which is less than 1. So the numerator stays fixed, but the denominator tends to infinity. So a fixed number over infinity is 0. So the limit of that is 0, which is less than 1. So by the ratio test, the series converges for all x. And the radius of convergence is r equals infinity. Okay.
Professor, could you
Yeah.
explain, like when you multiplied x to the n plus 1 times n factorial, how does it come out to be the absolute value of x?
No, so you're dividing by, you have x to the n plus 1 divided by x to the n. That's x. This divided by this.
Wait, why would it divide? Wouldn't you just multiply?
Look, you see, how, right? You would take x to the n plus 1 divided by x to the n, right?
Mhm.
See that?
Yeah.
And that's x, right?
Yeah.
And then n factorial over n plus 1 factorial is n plus 1.
Oh, okay.
See it? Makes sense?
Yeah.
And then the absolute value sign, I only put around x because n plus 1 is positive. So its absolute value is itself. And so you only need the absolute value there.
Okay.
Okay, good. Okay, good. You get it. Okay, so that. Okay, so so our conclusion is that if though it does, but right so far what we know is this: if e to the x has a power series representation, power series expansion representation at 0, then what it is e to the x is equal to the sum from n equals 0 to infinity of x n over n factorial. Okay, so with the assumption it has a power series representation at 0, we then conclude that that's what it is. Okay, and so that leads to the obvious question of how do you know if whether or not it has a power series representation, right? Okay, so the question is, how can we determine whether e to the x has a power series representation? Okay. Okay. And so in order to do that, we ask another question. What circumstances is a function equal to the sum of its Taylor series? Okay. Okay. In other words, if f has derivatives of all orders, when is it true that f of x is equal to the sum from n equals 0 to infinity of the nth derivative of f at a over n factorial times x minus a to the nth power. Okay, so if f has derivatives of all orders, when is it true that f of x is equal to that sum? Okay. Okay, so to do that, let's look at the partial sums, which we're going to call t sub n of x. So t sub n of x is equal to this sum, except instead of it being the entire infinite sum, we're going to start at I equals 0 and stop at n. And so we're going to take the sums using I as an index. So the t sub n of x is equal to the sum of the terms from I equals 0 to n. Okay. Okay, and so if you find that sum, it's equal to, and so you just plug in, so for I equals 0, you get that. For I equals 1, you get that times x minus a plus f double prime of a over 2 factorial times x minus a squared plus dot 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 plus the nth derivative of f at a over n factorial times x minus a to the n plus dot dot dot. Okay, so then we have that sum. Okay. Oh wait, so then we stop at the nth term. Okay, so that's t sub n of x. Okay, so t sub n is a polynomial of degree n called the nth degree Taylor polynomial of f at a. Okay, so in the example of f of x is equal to e to the x, we have that t sub 1 of x is equal to 1 plus x. Okay, because the derivatives are all okay, so we have the,
Excuse me, Professor.
yeah,
What does the exclamation point mean again? I forgot.
it's factorial, right? So I'll write that over here. So I'll remind you again. Okay, so reminder, n factorial is equal to the product of 1 times 2 times 3 times 4 times dot, dot, dot.
Okay, thank you. Thank you,
You're welcome.
Professor.
Welcome times n, right? That's n factorial. Okay, so that's n factorial. Okay, so the example of x equal to x, we have the Taylor polynomials at 0, or Maclaurin polynomials with n equals 1, 2, 3 are the following. So just go this way. This way. Okay, so the first Taylor polynomial at 0 is this because a is 0, right? So if you plug, you get 1 plus x here. Now, so if you have t sub 2 of x, this is equal to, you stop at 2, and so you get 1 plus x squared over 2 factorial, and so you get that. So if you have t sub 3 of x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so you get that. Okay, so you just take up to the nth term for n equals 1, 2, 3. And so these are the Taylor polynomials at 0. Okay. All right. In general, f of x is the sum of its Taylor series. If f of x is equal to the limit as n approaches infinity of t sub n of x. Okay, so if you take the sum of the first up to the nth term, right? Then if you take the limits n approaches infinity of that, you now have the entire infinite sum. If f of x equals that, it's equal to its Taylor series. Okay. Okay. Now let r sub n of x equal to f of x minus t sub n of x, so that our function f of x is equal to t sub n of x plus r sub n of x. Then r sub n of x is called the remainder of the Taylor series. Okay. If we can show that the limit as n approaches infinity r sub n of x is equal to 0, then it follows that the limit as n approaches infinity of t sub n of x is equal to the limit as n approaches infinity of f of x minus r sub n of x. Okay, so t sub n of x is now equal to f of x, right, minus r sub n of x from that equation, how we defined it. And so taking the limit of t sub n of x means taking the limit of that difference. But what is the limit of that difference? F of x, the limit of f of x is itself, and it's minus now the limit as n approaches infinity of r sub n of x. Okay. So if we show that the limit of r sub n of x is 0, then it follows that this is equal to f of x minus 0, which is f of x, right? If the limit of the remainders is 0, okay, so try to get back to normal size. Okay, so then if the limit of this is 0, then the limit of t sub n of x is f of x. Okay, and so what we have proved is the following theorem, that if f of x is equal to t sub n of x plus r sub n of x, where t sub n of x is the nth degree Taylor polynomial of f at a, and limit as n infinity r sub n of x is equal to 0 for solutions to x minus a less than capital R, then f is equal to the sum of its Taylor series. On the interval x minus a strictly less than R. Okay, so if f of x is equal to t sub n of x plus r sub n of x, where t sub n of x is the nth degree Taylor polynomial of f at a, and that the limit of the r sub n's is 0 in this interval, then f is equal to the sum of its Taylor series on that same interval. Okay, so the r sub n of x's are the remainders, right? And so if the limit of the remainders is 0, that means there's no difference between the limit of Taylor series of the nth degree Taylor series and the function f of x. Okay, and if the limit of the remainders is 0, then the limit of the t sub n's is equal to f of x. Okay, here's another theorem. Okay, it's called Taylor's formula. Okay, if f has n plus 1 derivatives in an interval capital I that contains the number a, then for x in the interval capital I, there is a number z strictly between x and a, such that the remainder term in the Taylor series can be expressed as r sub n of x is equal to the n plus first derivative of f at z divided by n plus 1 factorial times x minus a raised to the n plus 1 power. Okay, so this is Taylor's formula. If f has n plus 1 derivatives in an interval I that contains the number a, then for x in that interval I, there is a number z strictly between x and a, such that the remainder term in the Taylor series can be represented in this form. The z goes here, and this is still x. So there's a z and x here. It's not a typo. Okay, note. Okay, so note that the only thing we know that we say about z is that it is strictly between x and a. So the z in the theorem is not exactly known / pinpointed. Okay, so the z referred to in the theorem is just some z between x and a. So you can't plug in a value for z. Right? You can't say z is equal to, somewhere in between the mean or something. You can't say z is anything. The only thing you know about z is that it's between x and a. You can't plug in values for z and reach conclusions from it. Okay. Okay, so let's put another important fact. And so this is fact 11 in this section. And the fact is that the limit as n approaches infinity of x to the n over n factorial is equal to 0 for every real number x. Okay, so it doesn't matter which x we're talking about. If you take the limit as n approaches infinity of any number to the n over n factorial, it's equal to 0. Okay, the denominator increases way faster than the numerator. Even though they both tend to infinity, the denominator wins the race and the fractions tend to 0. Okay. Okay, so example 2. Prove that e to the x is equal to the sum of its Taylor series. Okay, so this example will complete the stories because earlier we found the Taylor series for e to the x, right? But we didn't show that it equaled the sum of its Taylor series. And so now we're going to do that. Okay, so let f of x equal to e to the x. Okay, and okay, so whoever's making that noise, I muted you. Okay, please stop making noise. Okay, so then if you take the n plus first derivative of f at x, it's equal to e to the x. So the remainder term in Taylor's formula is r sub n of x, which is equal to e to the z over n plus 1 factorial x to the n plus 1. Okay? Because the derivatives are all e to the power, right? So you have e to the z here. Okay, so that's the remainder term. And this is where z lies between 0 and x. Okay, note that z depends on n. Okay, so the z you have here is for each separate n. So each separate remainder term, each different n will have its own z between 0 and x. Okay, now if x is positive, then 0 is less than z less than x, because z is between 0 and x when x is, right? So z is positive here. So e to the z is strictly less than e to the x. That's because the exponential function is increasing. Okay? As you increase the input, the output gets bigger. And so since z is smaller, it gives you a smaller output, right? So e to the z is less than e to the x because the exponential function is increasing. Therefore, 0 is strictly less than r sub n of x, which is equal to e to the z over n plus 1 factorial, because we know that e to the z is positive, right? So actually, we also know that e to the 0 is strictly less than e to the z, strictly less than e to the x. E to the 0 is 1. Okay, so we know e to the z is greater than 1 and less than e to the x. Okay, so this is greater than 1, and 1 is also greater than 0, right? So we know that, we know e to z is always positive, actually. So, okay, so this is positive over that, and it's times x to the n plus 1 power, which is strictly less than, well, e to the x is bigger over the same denominator. Okay, but I'm just going to e to the x, and then I'm going to put here, I'm going to move the terms around a little bit, so we'll get x to the n plus 1 over n plus 1 factorial. Converges to 0. Okay, because before we showed that something of this form converges to 0, and so this, which is fixed, times that converges to 0. Right, and so since r sub n of x is sandwiched between 0 and these terms, and the limit of these terms is 0, and the limit of zeros is 0, that means that the limit of r sub n of x is 0. That means so r sub n of x converges to 0 as n approaches infinity. Okay, because it's sandwiched between 0 and this, and they both tend to 0, and so r sub n of x tends to 0. This is by the squeeze theorem. Okay. Now, this was if x was positive, right? If x is negative, then x is less than z less than 0, because z is strictly between 0 and x. And so that means that e to the z is strictly less than e to the 0, because it's still an increasing function. And e to the 0 is 1, right? And we have that the absolute value of r sub n of x is strictly less than, well, you now plug in 1 here for e to the z, right? And so now you get x to the n plus 1. You get the absolute value of x raised to the n plus 1 power divided by n plus 1 factorial. Okay, but then that also converges to 0, because anything of this form converges to 0. And so, and so that means that the absolute value of r sub n of x converges to 0. Okay, so yeah, that means that the absolute value of r sub n of x converges to 0. And so if the absolute values converge to 0, that means the terms themselves have to converge to 0. And so then that converges to 0 also. Okay. Right. And then if x equals 0, because we didn't consider that, if x equals 0, then, and then if x equals 0, right, e to the x is equal to e to the 0, which is 1. And the Taylor series representation right. Oh, so then just then, not even that. I don't have to do that. You could just say that r sub n of 0 is then equal to this, but x is 0. So you can actually evaluate this because it's 0. So you get 0 raised to the n plus 1, and then that's 0. Okay, and so since r sub n of 0 is 0 for all n, that means that the limit as n approaches infinity r sub n of 0 is equal to 0, right? This is 0 for all n. And so that limit is 0, right? And so we also get the same thing there. And so our conclusion is that e to the x is equal to the sum of its Taylor series. Okay, and so we showed it's equal to the sum of its Taylor series. And so e to the x is equal to the sum of its Taylor series. And so its Taylor series centered at 0, or its Maclaurin series, is this. Okay, now e to the x is equal to the sum of its Taylor series, which is that, because the limit of the remainders is 0. Okay. Okay, now if you plug in x equals 0, sorry, x equals 1, you get that e to the first, which is e, is equal to the sum from n equals 0 to infinity of, well, x is 1, x to the n is always 1, and so you get 1 over n factorial. Okay, and so that sum is equal to 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus. Okay, and so that's e. Okay, so another example, example 3. Find the Taylor series for f of x is equal to e to the x at x equals at a equal to 2. Okay, so now we want it centered at 2. Okay, so again, if we take the nth derivative of f at 2, we get its e squared, right? Because nth derivative of f at x is e to the x, and so you plug in 2, you get e squared. Okay, and so, and you get that the sum from n equals 0 to infinity of the nth derivative of f at 2, because it's centered at 2, over n factorial times x minus 2 to the nth power. That's the Taylor series representation. That's equal to the sum from n equals 0 to infinity of e squared, which is the nth derivative of f at 2 for any n, over n factorial times x minus 2 to the n. Okay, so it can be verified that the radius of convergence is r equals infinity. Okay, and so that means that this sum converges for all x. Okay, we can also verify that the limit as n approaches infinity of r sub n of x is equal to 0. Okay, so we know that it converges everywhere. The sum converges everywhere of the Taylor series, and we know that the function e to the x is equal to its Taylor series from this limit is 0. And so putting that all together, we know that e to the x is equal to its Taylor series centered at 2. And so its Taylor series centered at 2 is this. And this is for all x. Okay, for all x, because it's radius of convergence. The radius of convergence of this series is infinity. Well, it converges for all real values of x. Okay, so the Maclaurin series, which is the Taylor series centered at 0, is better if you are interested in values of x near 0. Okay, the Taylor series centered at 2 is better if you are interested in values of x near 2. So before, when we talked about the remainder, you can think of the remainder kind of how far away your nth degree Taylor series is from the entire infinite Taylor series, right? And so if you want to look at the values of your Taylor series near x equals 2, you would probably want to center it at 2. Okay, we'll go into more discussion on that. Another example. Example 4. Find the Maclaurin series for sine x. And prove it represents sine x for all x. Okay, so find the Maclaurin series for sine x and proves it represents sine x for all x. Okay, so first let's find the derivatives of f of x. Okay, where f of x, we're going to let f of x equal sine x. So let's find the derivatives. So you have f of x equals sine x. The first derivative, f prime of x, is equal to derivative, which is cosine x. The second derivative, f double prime of x, is equal to derivative of that, which is negative sine of x. Okay. The fourth derivative of f at x is equal to derivative third derivative. Third derivative f at x is equal to the derivative of negative sine x, which is negative cosine x. And the fourth derivative of f at x is equal to the derivative of that, which is again sine x. Okay. Now, if you evaluate them at 0, you get f of 0 is equal to sine of 0, which is 0. If you evaluate this at 0, you get f prime of 0 is equal to cosine of 0, which is 1. Okay, f double prime of 0 is equal to plugging in 0 here, which is negative sine of 0, which is 0. You take the third derivative of f at 0, and you plug this in, you get negative 1. And then the fourth derivative of f at 0 is equal to sine of 0, which is 0. Okay. Okay. Now you see that there's a pattern. We start to see it's shown once, but if you keep going, you have 0, 1, 0, negative 1. Then it'll go 0, 1, 0, negative 1, 0, 1, 0, negative 1. So the first 4, this pattern repeats 0, 1, 0, negative 1. Okay. Okay. So we get a pattern of 0, 1, 0, negative 1, 0, 1, 0, negative 1, and so forth. So we get a repeating pattern of here, okay? And so from that, we can write the Maclaurin series as follows. So if you have f of 0 plus f prime of 0 over 1 factorial plus f double prime of 0 over 2 factorial. And this is x squared. This is x. Okay. Plus, if you take the third derivative, f at 0 over 3 factorial times x cubed plus dot, dot, dot. And this is equal to, because now we have this pattern here. So we have 0 for f of 0. We have 1 here. So we have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. Okay, because this becomes 0, this becomes 0. All the even powers become 0. So you only have odd powers now. And the odd alternate between 1 and minus 1. So you have positive x minus x cubed, positive x to the 5th minus x to the 7th. And then the denominators are just 1 cubed. I mean, 1 factorial, 3 factorial, 5 factorial. So you see the factorial skip and the power skip and the sign skip. Okay, so you get this pattern here from this repeating pattern here. Okay, now this is equal to the sum from n equals 0 to infinity of -1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. Okay, I'll put this in front, -1 to the n. There we go. Okay, and so this is how you would represent this sum, because it starts at n equals 0, so you have positive, negative, and then you start with the power x to the first, but each time you increase the power by 2, so it's 2n plus 1. Every time you increment n by 1, you're adding 2 more to the exponent. And the same in the denominator, you're adding 2 more to the thing you factorial. So this is 1 factorial, 3 factorial, 5. So that's why you have 2n plus 1. Okay. Using the remainder term with a equals 0, we have, so the remainder term, where was the r sub n of x? So what we have is that r sub n of x is equal to n plus first derivative of f at c over n plus 1 factorial x to the n plus 1. Okay, and so we have that term. Okay, where this is where f of x is equal to sine of x, the original function, and z lies between 0 and x, because it's between a and x and a is 0. Okay, but the n plus first derivative of f at z is equal to plus or minus sine of z, or plus or minus cosine of z. Okay, because when we took the derivatives, right, we had plus or minus cosine. And so if we take the derivatives at z, it's plus or minus sine or plus or minus cosine. Okay, in either case, in any case, it's technically 4 of them. In any of those 4 cases, the absolute value of the n plus first derivative of f at z is less than or equal to 1, the absolute value, because the absolute value of sine and cosine is always less than or equal to 1, and the plus or minus doesn't change the absolute value. Okay, so that means that 0 is less than or equal to the absolute value of R sub n of x, and which is equal to the absolute value of the n plus first derivative of f at c over n plus 1 factorial times the absolute value of x to the n plus 1. Okay, because we have the absolute values of this, but we now have this inequality. It says this is less or equal to 1. And so this is less or equal to the absolute value of x raised to the n plus first power divided by n plus 1 factorial, because this is now less or equal to the 1 there. Okay, now the limit of this is 0, right, as n approaches infinity. Okay, right, because when anything of this form, a number raised to this over this factorial converges to 0. Okay, and that means that the absolute value of R sub n of x converges to 0. So this thing converges to 0 by the squeeze theorem. Right, and if you have the terms of a sequence, the absolute value of the terms of a sequence converges to 0. That means the terms of the sequence also converge to 0. And so that converges to 0. And this is still as n approaches infinity. Okay. Okay. And so sine of x is equal to the sum of its Maclaurin series, because the limit of the R sub n of x's are 0. It's 0. Okay, and so keep in mind, important note, that if you want to express sine of x as its power, find the Taylor series representation of sine of x, it looks like this. This is for all x. All right, and so that's how you represent sine of x as find the Taylor series representation of sine of x, and it's equal to that representation. Okay. So now, as an important, so you can follow a similar procedure for cosine x, and you can reach this conclusion. And so this is also important. The representation of cosine x is the following: cosine x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot dot dot. And that's equal to the sum from n equals 0 to infinity of negative 1 to the n times x to 2n over 2n factorial. And this is for all x. Okay. And so now you can represent this also. This is the Maclaurin series representation. Okay. This is the Maclaurin series for cosine x. Okay. It's centered at 0 because you have x minus 0 squared, x minus 0 to the 4th, and so on. Okay, example 6 is find the Maclaurin series for the function f of x is equal to x cosine x. Okay, so for this, let's use the important fact that I already gave you. x cosine x is going to equal x times its Taylor series times its Maclaurin series representation here. Because cosine x is equal to that. So I substituted. And if you substitute that, then you're just taking the original powers and you're adding 1 to them. Okay, you're just adding additional x there. And so you get that's the power series. That's the Maclaurin series for f of x equals x cosine x. Okay. Okay. So another important fact. I'll put here. The Maclaurin series of x is equal to 1 plus x raised to the k power is the sum from n equals 0 to infinity of nth root of f at 0 over n factorial times x to the n. And that's equal to the sum from n equals 0 to infinity of denominator is n factorial, and then the numerator you have k times k minus 1 times dot 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 times k minus n plus 1. This is times x to the n. Okay. This series is called the Binomial Series. Okay, so finding the Maclaurin series for this function f of x equals 1 plus x to the k, you get this. And that's called the Binomial Series. Okay, using the ratio test, you can prove that the Binomial Series converges if the absolute value of x is strictly less than 1, and diverges if the absolute value of x is strictly greater than 1. Okay, and so the notation that's generally used is that you can use this notation to represent that strange expression. And so they're called combinations. K choose n is the notation that represents this. Okay, and so, and these numbers are called the binomial coefficients. Because of the coefficients of the x to the n terms here. And so our conclusion with all this is called the binomial. This is about binomial series. It says if k is any real number and the absolute value of x is strictly less than 1, then you get that 1 plus x to the kth power is equal to this sum, except we use this notation, right? We use this to represent that, right? And so you can just write that there. And so it's equal to that. And then if you expand this, you get 1 plus kx plus k times k minus 1 over 2 factorial x squared plus dot, dot, dot. Okay, so even though the binomial series converges when the absolute value of x is less than 1, question of whether or not it converges at the endpoints plus or minus 1 depends on the value of k. So for different values of k, you get different answers whether or not it converges at 1 or negative 1. Okay. Okay.
Professor,
Yeah.
when you have the parentheses k over n, is it like k divided by n?
No, it's this. So this is just notation. So
Oh,
this
okay,
doesn't. This can mean whatever it's defined to mean. So this is equal to that.
All right.
Okay, good question. Okay, so let's go to example 9. So part A is evaluate this definite integral. Evaluate the integral from 1 to negative x squared. Oh, sorry. Evaluate the indefinite integral of e to the negative x squared dx as an infinite series. Okay, and B, evaluate definite integral from 0 to 1 of that e to the negative x squared dx. Correct to within an error of 0.001. Okay. So let's do that. So solution. So for part A, first find the Maclaurin series for f of x is equal to e to negative x squared. Okay. And so to find the Maclaurin series, you just substitute negative x squared in for x into the Maclaurin series for e to the x. So this is n equals 0 to infinity of negative x squared to the n over n factorial. And so it would normally be x to the n, but since instead of e to the x, it's e to negative x squared, you substitute negative x squared here. Okay, and so then this is equal to the sum from n equals 0 to infinity of the denominator stays n factorial. Now the numerator, it's x, it's just x to the 2n because the negative sign, the negative 1 is being raised to the 2n. And so that goes away. So you get that. And then this is equal to 1 minus x squared over 1 factorial plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus dot, dot, dot. Okay? And so you get that sum. Now integrate term by term. And so what you get is that the integral of e to the negative x squared dx is equal to the integral of all this. So you're integrating that with respect to x. And so when you do that, you get integration constant plus now term by term, you integrate, you get x minus x cubed over 3 times 1 factorial. And then you have plus x to the 5th over 5 times 2 factorial, and then minus dot dot dot, and then keep going, and then it's plus negative 1 to the n times x to the 2n plus 1 over, and you have the 2n plus 1, and you have the n factorial. So you get this, and then plus dot dot dot. Okay. So now I've so for part A, right, evaluate that as an infinite series. Done. So for part B, the evaluation theorem, which is from the fundamental theorem of calculus, the evaluation theorem gives that the definite integral from 0 to 1 of this is equal to so it's equal to this entire sum, which is an antiderivative, evaluated from 0 to 1. Okay, so now this is equal to when you plug in 0, everything's 0, so it's really just evaluating 1. So it's 1 minus 1/3 plus 1/10 minus 1 over 42 plus 1 over 216 minus dot dot dot. And now that's equal, this is approximately equal to. Now if you add up those terms, so instead of saying the entire sum, if you stop at this term, and that's very close, and that's equal to 0.7475. Okay, and so the question said to show it's accurate within an error of 0.001. And so how do I know that? The alternating series estimation theorem shows that the error involved in this approximation is less than, it's less than the next term, which is 1 over 11 times 5 factorial. And that's equal to 1 over 1,320, which is strictly less than 0.001. Because it's less than 1,000, right? 1 over 1,320 is less than 1,000, less than 1 over 1,000, which is 0.001. Okay, and so that shows that. Okay. Okay, so example 11. Let's do example 11. Find the first 3 non-zero terms in the Maclaurin series for, and let's just do part A, e to the x sine x. Okay. So if you use the table that they give you in the book, right, you can quickly right ahead know that e to the x sine x is equal to the product of these two expansions, right? You have 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed 3 factorial plus dot dot dot. And then the Taylor series for sine x is x minus x cubed over 3 factorial plus dot, dot, dot. Okay. So we multiply these expressions, collecting like terms, just as for polynomials. Right? And so if you do that, you'll see that e to the x sine x is equal to x plus x squared plus 1/3 x cubed plus dot, dot, dot. Right? So eventually, if you go far enough out, the powers will be too high. They'll be at least to the 4th, right? So for instance, if you have x, you can only multiply up to x squared. Once you multiply by x cubed or any term higher, you'll get x to the 4th and on, right? You won't get the first 3 terms. And so here, x cubed, you can only multiply it by 1 to get a term in the first 3, right? Okay, so you only have finitely many terms you need to add to get the first 3 non-zero terms in the Maclaurin series. Okay? Okay, so that's 8.7. And the last section of the course is 8.8, which is application of Taylor polynomials. Okay. Okay, so this last section. Yay. And then, so we're going to talk about approximating functions.
Hey,
by
can you go up a
polynomials.
little bit, Professor?
Sure. There you go. Is that good? Okay, so suppose that f of x is equal to the sum of its Taylor series at A. So what that would mean is that f of x is equal to the sum from n equals 0 to infinity of enter of f at A divided by n factorial times x minus A, the nth power. Okay, so suppose that, right? So we also have the nth degree Taylor polynomial of f at A is t sub n of x, which is equal to the sum from I equals 0 to n of those terms. The ith derivative f at A over I factorial, just using a different letter for the index, same thing, same terms. I, right? Okay, so f is the sum of its Taylor series. We know that t sub n of x converges to f of x as n approaches infinity. Okay, so t sub n can be used as an approximation. As an approximation to f, right? Meaning that f of x is approximately equal to t sub n of x for sufficiently large n, right? The t sub n's converge to f of x as n approaches infinity. And so if you take an n large enough, you can get as close to f of x as you want. And so you can approximate it that way. Okay, so notice that the first degree Taylor polynomial t sub 1 of x is equal to f of a plus f prime of a times x minus a. Okay. Uh, okay. This is the linearization of f at a. Okay. And so near x equals a, the linearization of f at a is very close to the graph of f. Okay. And so we can see it as an approximation of our function. And so this linearization of f at a approximates f of x near a. Okay. Okay. And so since, okay, so let me put this way. If you look at the absolute value of the remainder, r sub n of x, it's equal to the absolute value of f of x minus t sub n of x, right? It's called the remainder. So that's how far away f of x is from t sub n of x. And so what we want to do is we want to make r sub n of x, the absolute value of r sub n of x, very small. That way the error is small. Okay. So let's look at an example. Example 1, part A. Approximate the function f of x is equal to cubed root of x by a Taylor polynomial of degree 2 at a equals 8. Okay, and then part B is going to be how accurate is this approximation when 7 is less or equal to x less or equal to 9. Okay, so let's go through this example. So solution. A. So let's just list the function its derivatives. So let's f of x, let f of x be the cubed root of x. And that's equal to x raised to the 1/3. Okay, using exponential notation. Now if you take the derivative of that f of x, you take the derivative, you get 1/3 x to the negative 2/3. Okay. And then if you take the derivative again, you get f double prime of x. And that's equal to the derivative of that, which is negative 2/9 x raised to the negative 5/3. And then if you take the fourth derivative, take the third derivative f at x, it's equal to 10 over 37 x raised to the negative 8/3. Okay. And if you evaluate them at 2, I mean at 8, sorry. If you evaluate them at 8, you get f of 8 is equal to cube root of 8, which is 2. And then if you do f prime of 8, that's equal to 1 over 12. And if you do f double prime of 8, it's equal to 2 to the 5th in the denominator is 32. So you get negative 2 over 9 times 32. So you get negative 1 over 144. Okay.
Wait, Professor?
Yeah.
In the test, if you have a question like this, you'll be allowed to use a calculator, right?
Yeah, you can use a calculator.
All right. Just making sure, because like the math you're doing is kind of like complex and stuff.
Okay, yeah, you
Right.
can use a calculator. Okay,
Yeah, thank
so
you.
thus the second degree Taylor polynomial is t sub 2 of x, which equals f of 8 plus f prime of 8 over 1 factorial times x minus 8 plus f double prime of 8 over the 2 factorial times x minus 8 squared. Okay, so you just plug in the values I gave. So you, f of 8 is 2, 2 plus f prime of 8 was 1/12, 1/12 times x minus 8 plus f double prime, and so now you have minus 1 over 144 times 2 for the 2 factorial, you get minus 1 over 288 times x minus 8 squared. And so that's that. That's t sub 2 of x. The desired approximation is, that take the cubed root of x, and this is approximately equal to t sub 2 of x, t sub 2 of x, which is equal to that. Okay, so we took t sub 2 of x as our approximation for the cubed root of x. That's A. And B, okay, so note the Taylor series is not alternating when x is less than 8, right? And so we can't use the alternating series test. It's alternating series estimation theorem in this example. Okay, but using Taylor's formula, you can write, say that r sub 2 of x is equal to this third derivative of f at z over 3 factorial times x minus 8 cubed, right? Which is equal to 10 over 27 times z raised to the negative 8 thirds times x minus 8 cubed over 3 factorial, which is equal to 5 times x minus 8 cubed over 81 z to the 8 thirds. Okay. And so we have that. So r sub 2 of z, r sub 2 of x is equal to that. And this is where z lies between 8 and x. Okay. So in order to estimate the error, you note that if 7 is less or equal to x, less or equal to 9, then negative 1 is less or equal to x minus 8, less or equal to 1. So the absolute value of x minus 8 is less or equal to 1. And therefore, the absolute value of x minus 8 cubed is also less or equal to 1. Also, since the absolute value of z, since z is greater than 7, we have that z to the 8 thirds is strictly greater than 7 to the 8/3, because c is greater than 7, and z to the 8/3 is greater than 179. So the absolute value of r sub 2 of x is less than or equal to 5 times x minus 8 cubed. This is from over here. Divided by 81z to the 8/3. And that's strictly less than 5 times 1 divided by, so here's the 5, but we know the absolute value of x minus a is less than or equal to 1, and that the absolute of x minus a cubed is less than or equal to 1, so that's less than or equal to 1 there. It's less than, and then z to the 8/3 is strictly greater than that. So what that tells you is that 1 divided by z to the 8/3 is strictly less than 1/179, going in the opposite direction. And so this is strictly less than you have still the 81, but now you have the 179 here. And so that's strictly less than, when you calculate, that's strictly less than 0.0004. Thus, if 7 is less than or equal to x less than or equal to 9, the approximation in part A is accurate to within 0.0004. Okay, because the absolute value of the remainder is less than that. Okay, and so this is an example. This is an example of how to do that. Okay. All right, let's do another example. So stay with me for another few minutes, and then we're good. So I'm just going to do an extra example. A, what is the maximum error possible using the approximation sine x, which is approximately x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. When 0.3 is less than or equal to x, less than or equal to 0.3, negative. Negative 0.3 less than or equal to x, less than or equal to 0.3. Use this approximation to find sine of 12 degrees. To find sine of 12 degrees, correct to 6 decimal places. Okay, solution. Okay, so for the solution, we have the Maclaurin series. The Maclaurin series for sine x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot dot dot. That's the Maclaurin series. So Maclaurin series for sine x is alternating for all non-zero values of x. The successive terms decrease in size because the absolute value of x is strictly less than 1. So we can use the alternating series test. Sorry, alternating series estimation theorem. Okay, so the error in approximating sine x by the first 3 terms of its Maclaurin series is at most the absolute value of the next b term, which is x to the 7th over 7 factorial. And that's equal to the absolute value of x to the 7th power divided by 5,040. If negative 0.3 is less or equal to x, less or equal to 0.3, then the absolute value of x is less or equal to 0.3. So the error is smaller than 0.3 raised to the 7th power divided by 5,040. And that is approximately 4.3 times 10 to the negative 8th power. Okay, to find sine of 12 degrees, we first convert to radian measure. So I should note, I'm going to take a few more minutes, but I put the review to some of the problems on the review sheet test 3 online. If you go to test 3, there's a review sheet there for test 3. There's also a video where I go over some of the solutions. Also, if you go to the homework section, the last homework, 8.6, 8.7, 8.8, I have a typed up solution to all the problems, and I have a video going over all the solutions to it. Okay, so that's under homework, and under that for 8.6 to 8.8, I have typed up all the solutions and a video. So after this class, you do the homework, you can watch the video and read it, and I'll go through over how to do all the problems in the last homework. Okay, before the exam on Wednesday. Okay, so to find sine of 12 degrees, I first convert to radian measure. So sine of 12 degrees is equal to sine of 12 pi over 180. And that's equal to sine of pi over 15 radians. Okay? And so that's approximately sine of pi over 15 is approximately equal to, this is lowercase sine. This is approximately equal to pi over 15 minus pi over 15 cubed times 1 over 3 factorial plus pi over 15 to the 5th times 1 over 5 factorial. And that's approximately equal to 0.20791169. Okay, so thus correct to 6 decimal places. sine of 12 degrees is approximately equal to 0.207912. Okay. Okay, I'm going to do part B also. Okay, so for part B, it says for what values of x is this approximation accurate to within 0.0005. Okay. So for that, the error would be smaller than 0.0005, 0.00005 if the absolute value of x raised to the 7th power by 5040 is strictly less than 0.00005. Solving this inequality for x, we get that the absolute value of x to the 7th power is strictly less than 0.252, or that the absolute value of x is strictly less than 0.252 raised to the 1/7 power, which is approximately 0.821. Okay, so the given approximation is accurate to within 0.00005 when the absolute value of x is strictly less than 0.82. Okay, so what I went over, these examples illustrate what I want you to know about section 8.8. Okay, and so the homework for 8.8 was one problem, parts A and B. Okay, so for homework, you have 8.6, 8.7, 8.8. Okay, those are the last homeworks. Okay, online on Blackboard, after you do this homework, do it today, right? Go to the homework section. Well, you have to go to it anyway to see the homeworks, but go to the homework section, and there is a typed up Word document going over every solution. Also, I have a video there where I go over every solution from that Word document. Okay. Okay, so I'm going over all these homeworks, even though this is our last class for the test. Just watch the video after this class before the exam, and I go over every problem in those homeworks. Okay, so that covers all the homework. Again, so there's a review sheet online. You should be studying that. I put up the solutions to some of the problems online under the test 3 section. Okay, okay, and so a very important reminder, right? Test 3 is next class, during class, and it's right 1:40 to 3:30 p.m. 1:40 p.m. to 3:30 p.m. right on May 12th. May 12th, Wednesday, May 12th. Okay. right? Use the same Zoom link you always use, okay? To take tests or join class, okay? It's the same Zoom link. So that won't be a problem. Let me check really quickly for 1 second to make sure the Zoom link is good, but it is. Just want to be super 100% certain of this. Yeah, okay, good. So the link is all set up, so there's no problem there. Okay. Okay, so we're here. Somebody put something in the chat. So the test will be 1 hour long, okay? So test 3 is 1 hour long, okay? I will use the rest of class after test 3 to review for the final, okay? And also an important reminder, the final, remember, is on the last day of class on Monday, May 17th, at the start of class, and from 1:40 p.m. to 3:30 p.m. Okay, use the same Zoom link you always use to join class to take the final. Okay, to join the Zoom meeting for the final. Okay, so the final again is on May 17th, Monday, May 17th, during class. It starts at the start of class, 1:40 p.m. to 3:30 p.m. Okay, so there's no final during finals week for this class. It's on the last day of class. Okay. Okay, so again, I put up a Word document with all the solutions to the last homework, right? These homeworks, I put the solutions in the Word document. I also made a video going over every solution. I also made a little bit of a review for the third exam, and I put that video on there, okay? Okay, but you have the review sheet, and so you have all those problems, so you need to review them. And and then after we're done with the test, if there aren't too many interruptions, if we can finish the exam and get that done quickly, I can have more time to help you with the final, okay? And so we'll go over the final. If you want me to stay a little longer, I can on Monday. I have to go by maybe 4 o'clock or slightly after. But if you want me to stay longer, I would stay longer as long as I can to help you with the final also, okay? And also keep in mind that there is a office hour this Friday, right? And so if you have questions about the final, you want help with the final, I'm going to help you after the exam on Wednesday and stay after class as long as I can. And Friday, there's also office hour. And I have the review sheet online for the final, okay? Okay, so that's everything. Okay, any questions about anything? Any of that before I go? Okay, that's it. Okay, so that's the end of class. Thank you for being here. You too, have a good day. The stuff I put online, I tried to also put on YouTube. But I think the stuff I just talked to you about, it's on Blackboard. Okay. Okay, bye. You're welcome. Have a good one.